Okay, so today is Friday, September 25th. We had to deal with some internet outages, so my apologies for that. We were not able to conduct the lesson properly, so we have to put this thing on a video. Yeah. All right, so let's just, okay, get some good coffee. Now we're not going to rush. We're not going to have a stop and go session. Let's just take care of the PowerPoint, and then I'm going to show you some practical aspect of this lesson here, okay? All right. PowerPoint. Okay, so the common DMM symbols, this is the digital multimeter symbols. Voltage with a little tail D, that stands for AC voltage. That's for alternated AC, so alternating voltage, alternating current. You're going to learn about that in other subjects. If you want to measure DC voltage, then you switch to this symbol. And just let me just put this thing here, zoom on the real digital multimeter. So we do have those here. Just adjust the focus. All right, so here's the DC voltage, and the ranges are 1 kilovolt, so that's 1000 volts, up to 200 volts, up to 20 volts, up to 2 volts, and so on. And then there's the same thing for the AC voltage. Then there's AC current. Also, we have resistance, and here's a continuity meter, diode tester. I'm going to show you some cool stuff with that today. And then there is amp meter section right here. That's a multimeter. It can do more than one function. So this is one of the functions. You can also measure current. Now let's see at the port. Let's take a look at the ports. As we said last time, the black lead goes to the common, and that's usually considered as negative. If it's a DC, then the red goes into whatever else is being measured. So let's say this port right here is marked as voltage, resistance, and diode tester. So if you want to measure voltage, you are going to use this port. If you want to measure current in milliamps, so anything that says milliamps, so the range says up to 200 milliamps, up to 20 milliamps, up to 2 milliamps, or 200 microamps, that also fits there. Or okay, it just actually says here, you can measure milliamps or microamps. You're going to use this port if you want to measure current. Now, if you want to measure current not milliamps, like this amps, so this one says amps, 2 amps, up to 2 amps, up to 10 amps, you're going to use this port right here. So that's how this particular meter works. Of course, different meters might alter in some sort of way, so you're going to have to know your own meter here, okay? Now, let's go back to the PowerPoint right here. Okay. All right. So millivolts. So we went over that. You probably have this thing downloaded already because it's available for download because it was available right after the scheduled time for the lesson to be finished. Anyways, other symbols. The one that doesn't show on that meter that we have here is the capacitance meter. Some meters do have the ability to measure capacitance, but then again, you're gonna have to know whatever the particular meter is that you are using, okay? There was a little bit of a note. These symbols are often found in multimeter and schematics. They are designed to symbolize components and reference values. It's pretty much self-explanatory. Okay, let's keep going. Measuring voltage. I'm going to go through these slides and then I'm going to show you the practical side of this, okay? So voltage, electrical pressure, difference of potentials. That's what voltage is. Okay? Later on, I'm going to show you another site that I go a little bit in more detail on what voltage is, and it is actually there's actually a link right in this PDF document that you're going to have. All right, it's available for download on FOL. Okay? So 1 volt is the difference of potentials needed to cause 1 amp of current to pass through 1 ohm resistance. bit of a definition here. Voltage is divided into two sections, AC and DC. AC stands for alternating current found in house voltage in your outlets. In your wall outlet, we have 110 volts AC. All right, the other one is direct current. Direct current is basically, it has a clearly defined negative or ground reference or neutral, and clearly defined positive or clearly defined negative. So let me just go to the board here. So the difference between AC and DC is, if you have, let's use the green here. It reflects nicely. I'm just going to lower the lighting a little bit so we can see things better. All right. So when we have DC, direct current, okay, here is a ground reference, okay, it will be 0 reference. And over here, you could have the y-axis here. And over here, you could have the current going, or the voltage stay at, let's say, 10 volts, or stay at 5 volts. And it's not going to go below on the other side of that. It's a DC, direct current. Also, what it could be a negative DC. So you could have 0 reference right here. You could have negative 5 volts. You can have negative 10 volts. And that means that voltage is going to stay between here and here. It's not going to go on the other side of the reference here, okay? Now, if it comes to AC, it's a bit of a different story. Let me just erase this thing here. Alternating current. Okay. Now, when it comes to alternating current, we're going to have a reference of 0. Okay, and then we have y-axis. So here's x-axis, y-axis here. So this is our 0 reference, and alternating current is my vary between positive and negative reference of that. So that would be alternating current. Right? So that's the difference between AC and DC. So this is alternating current here, or voltage. So this would be voltage. This would be 0 reference. Okay? And this would be time, okay, over time. So let's just take care of something else. You could have something like this here. Okay, now is this AC or DC? Well, this would be a DC, okay, because it never, the voltage never goes on the other side, right? When we're making power supplies, you're going to smooth things out. This would be a pulsating AC. You're going to if you rectify it, you're going to have something like this. That's also DC already, but it's pulsating DC. All right. Now you can smooth things out with capacitors. You can have something like this. All right. So now you're going to have AC element riding on the DC reference. So this will be the average right here. So you have 2 elements here, AC with a reference of like 5 volts. Okay, so it will be AC riding on the 5 volt reference. But the whole thing, as the whole waveform, that's not AC anymore as a whole. It's just still DC because it stays on one side of the reference. Okay. Now I'm just gonna erase that here. All right. Let's just get rid of the. Okay. I'm going to go back to our slides. All right. For the most accurate reading, while selecting the range of switched meters, the high-end volume of the range must be one step higher than the measured voltage. What does this mean? Let's see what does this mean. Okay, I'm going to switch to this view right here. Zoom on one of the meters. Okay. Now, I have selected here, the 20 volts range on the DC voltage. Okay. Now, let's turn this thing on. What I'm going to do is I'm going to set my power supply to 5 volts. Can you see that? Here's my power supply sitting at 5 volts. Okay. Now we're going to measure the voltage with this multimeter. Do we have a range that is 5 volts? No, what's still lower than 20? It's 2 volts. We cannot measure 5 volts when the range is selected to up to 2 volts because it's just going to show us. Let's see what this meter, I'm going to take these probes and I'm going to put it right across the power supply. Here, okay. What do we get? Voltage here. All right, we get something like this. You see that 1 and a dot? That means we're out of range in this particular meter. In some of the meters, you're going to see OL, like over limit or overload or something like that. Now, okay, so we are measuring 5 volts. So we're going to go next one. So this is 20 volts. Can we measure 5 volts with 20 volts? Yes. So let's see here. I'm going to put the leads across the power supply, and this meter shows 5.02 volts. Okay. Now, can we measure the voltage with the 200 volt range? Yes, we can, but we are not going to get as accurate reading as if we selected 20 volts. You see, this one shows 5.0. The decimal point has shifted. Okay. So this is 5.0 volts. It doesn't show the 5.02. But if we go to the range that is just over 5 volts, you see the decimal point has shifted here, okay? Then we're going to get a little bit more accurate reading. It's going to show us 5.02. So when you're measuring voltage, let's say whatever it is, go to the closest one and next over. Okay, so 5 volts, the closest one will be, and next over would be 20, because with 2 volts, up to 2 volts, we can't measure that. Next one is going to be 20. Okay, and try to stay at the closest one. So the measured voltage is the closest to the range, but the range has to be bigger than the measured voltage. Okay. All right. So we took care of that. The probe tips must be in contact with only the measured test points and nothing else. Yeah, okay. Sometimes people are going to measure voltage and they're going to hold the probes like this. You're putting yourself in a circuit with that. If there is a voltage higher than 30 volts, then it actually becomes lethal to you, okay? So, and you don't want to even measure the 100 volts like that, because that current is going, you're putting yourself in the circuit. You're touching those probes while you are measuring something. So that's why we have those probes. So we could hold on to these probes. Now, if you're measuring higher voltage, try not to use both hands, because if there's any break, if something is damaged, maybe there could be a damage in those leads here, and you're going to be touching your hands, then the current is going to go through you. It's just an extra safety. So if you were measuring that, just hold it with one hand. That's a technique of holding with one hand. And what's happening with the other hand, you just hold it in your pocket. Okay, or make sure, because that way you're making sure that you're not going to touch anything else with your other hand, so the current doesn't go through you. Okay. Now, in the internal resistance, of a voltmeter is extremely high. so the measurement can be taken without affecting the circuit ideally, typically in the neighborhood of 10 mega ohms or higher, okay? And let's see, maybe the next slide is going to show, yeah, okay? So what happens here, first we're going to have the circuit without the voltmeter. So here's the circuit, okay? Here's the power supply. The current flows through from the positive. This is the conventional current flow. The current flows from the positive side of the power supply this way through one component and then through the other component and comes back right to the power supply, okay? Now, if we want to measure the voltage across this resistor here, R2, we are going to put the voltmeter in parallel to that load. So obviously, we're providing one more current path here because the current is going to go from here to this R1. And then over here, there's a node, so the current is going to split. Part of the current is going to still keep going through this main circuit, and part of the current is going to go through the voltmeter. So that's why the voltmeter internal resistance, while measuring voltage, the voltmeter, its resistance has to be extremely high. What's the highest resistance? Okay, over here we have also high resistance across this resistor and high resistance across that resistor. It's the resistance of air, okay? It's extremely high. Now, we also want to have extremely high resistance of the voltmeter. So if the resistance is extremely high, then the current flowing through this voltmeter is going to be extremely low. So we're taking a tiny, tiny bit of a sample of the current, and it's so tiny that it's insignificant to the circuit, to the whole circuit. It's not really affecting the circuit here. It's just a tiny, tiny, itsy-bitsy amount of current, just to take a sample, just to trigger the measuring mechanism, whatever that is. It could be analog, it could be digital sampler. All right, so that's why. So that's why the resistance of a voltmeter has to be extremely high, because we're sticking that thing in parallel to the load. The voltmeter is connected in parallel with the measured load. Now, just a little bit of a word of advice. Whenever you're going to assemble circuits in your other subjects, try to take care of the current path first, because if you see schematic, you're going to have, okay, you need to connect wire from here to here, and then from here to here to here to here. Okay, forget the parallel devices first, like, so for example, the voltmeter. Take care of the current path first while you're assembling a circuit on the breadboards or wherever else. And then after you take care of the current path or pathways, then the next thing is just add on with the parallel devices. It's going, if you stick to that way of connecting circuits, it's going to be much easier for you to either connect the circuits or verify if somebody has, because sometimes in different subjects in my classes, when I do, I used to have two people. One person is assembling the circuit and the other person is going to verify. So if you verify the circuit, you're just going to verify the current path first and then make sure that the parallel devices are connected to it, okay? All right, measuring voltage, again, because the internal resistance of the voltmeter is extremely high, then you can stick it stick the probes or apply the probes right onto the load, and that is going to measure the voltage across this 9-volt battery. You will not do it. You would not do this with the amp meter. If you connect an amp meter like that, you're going to run into some trouble, and we're going to show you how. All right, the next thing is we're going to take measuring resistance, okay? So a little bit of resistance. Resistance, with the symbol of R, is the opposition to the current flow, and the current is symbolized with the letter I, okay? Then I should probably put this R in the regular parentheses, not the square brackets. I like to use the square brackets when I am describing units. So this here should not be in the square brackets, right? Unit for the resistance is ohm, and sometimes you're going to see a written unit like that, or sometimes you're going to see the omega sign. It's going to be the same thing. It's a Greek letter of omega. That's how you pronounce that. And since it's the closest phonetically sounding letter to ohm, this is how somebody with somebody else, and they decided that this is what's going to be used as a unit. Yeah, pretty cool. Anyways, all right, let's keep going. The quantity that is opposite to resistance is called conductance. All right, so an object could have certain amount of resistance or certain amount of conductance, and conductance and resistance are inversely proportional, which means the symbol G, the letter G stands for conductance. G equals 1 over R. So conductance equals 1 over resistance. So that means that they are inversely proportional. This is the relationship between that. And the unit for conductance is S for Siemens. Okay. Then a little bit of a definition here. If a current of 1 amp passes through a component across which a voltage is 1 volt, then we can say that the conductance of this component is 1 Siemens. All right. Procedure of measuring resistance. Disconnect the power source or de-energize the circuit. You have to de-energize the circuit. First thing, you cannot measure resistance in a circuit that is powered. You just cannot do that. The reason for that is, excuse me, is because the the ohm meter, when you switch the multimeter to be an ohm meter, that ohm meter produces a tiny bit of a voltage across its probes. So I'm going to show you this. Here, I have 2 multimeters of the same kind. And one of them, I'm going to, focus, good, it's good. All right, one of the multimeters I'm going to set to a ohm meter. Let's say up to 2 kilo ohms, which is up to 2000 ohms. So this multimeter right now is configured as a, this DMM, digital multimeter, is considered as a ohm meter here, okay? And the range we have selected is up to 2000 ohms, 2 kilo ohms. Now, of course, why do we show the overload or out of range? We are measuring out of range. Well, because the probes that we have are not connected to each other, okay? What is between them? Between those probes, there is resistance of the air, and the resistance of the air is extremely, extremely high, much higher than 2 kilo ohms. So it's correct, the display shows correct. We're having much greater resistance than 2 kilo ohms across the probes. Now, how does the ohm meter measure resistance? It is going to introduce a tiny bit of voltage across the probes, across the tips, and which is going to make the current flow from one probe through the resistor to the other probe. Okay, now let's take a look at what is the voltage that this one. So the other multimeter, I have set it up to as a voltmeter. So using this voltmeter, I'm going to measure the voltage across these 2 probes when it's configured as a ohm meter. So let's just take a look at that. Okay. I can hold this like that for now, but the other one, I'm just going to make sure that I'm not touching anything else here now. So let's just take a look at that. Oh, when it's set up to 2 kilo ohms range, this multimeter is going to have 0.6 volts across its probes. Now let's see if it's true for other ranges as well. All right, 200 ohms. Oh, when you switch it to 200 ohms, it produces a little bit more voltage. Okay, so right now, this meter is configured as ohm meter. It's going to introduce 2.4 volts across its probes, so it can pass the current through the measured resistor, And this way you can measure the resistance of the resistor here. Okay. Now, so that means what's the procedure here? Disconnect the power of the source before. So, okay, let's get this thing. Let's say we have a circuit. Okay. Here's a power supply, plus, minus. Okay. Lower the light a little bit. That's better. Okay, and over here we have a line that is going to a first resistor. We're going to call this R1. Then we're going to the line continue and go to another resistor, R2, and we're going to go and close the circuit, maybe with a switch. And the switch is going to be closed. Also, what we're going to do is we're going to apply another resistor in parallel with R1. And that is going to be R3. Okay? So let's say we need to measure the resistor. We want to measure, we're going to verify that the value of the resistor is what it should be, because for some reason we need to check this resistance, which is in the circuit. Now, so we're going to have an ohm meter. Okay, and we're going to connect this like so. Is this correct? It is not correct. First of all, the circuit is not de-energized. There is going to, because there is going to be a current flow through this resistor, that means there is going to be a voltage across this resistor when the circuit is energized. This voltage is going to start fighting with this voltage that is introduced by the ohm meter, and we're going to have some conflict of voltages, as a result of which probably you're going to damage this ohm meter here. Okay? So we need to, first we need to de-energize the circuit. Okay? So we're going to open the switch. Okay? Now there's no current flow. The circuit is de-energized. Can we measure the resistance of this R1? We still can't, because even though there is no pathway going here, but there's some other thing that is connected to this resistor. So if we measure that, if you just want to measure that resistor R1 value, we need to disconnect that from that one, from the R3. What do we do? What can we do? Well, let me just get rid of this line here first. And I'm going to just break this line right here. Okay? So now this resistor is not connected to anything else. Can we measure it now? The circuit is de-energized, and the resistor is taken out of the circuit. Even if the circuit was energized, there is no current flow through this resistor. However, we should de-energize the circuit, because now we are removing one part, one component out of the circuit. And sometimes when we remove a component out of the whole circuit that's not supposed to be working as a whole, then you can actually damage whatever the circuit is by removing a part. Not always, but sometimes you can do that. Sometimes it happens. So de-energize the circuit, disconnect the resistor. Now this resistor is still connected on this side here. However, it doesn't have a closed path with anything else. So that's considered something that you can say lifting one leg. Someone's going to say, if you want to measure a resistance across some component, all you have to do is lift one leg, which means we broke one. We could just do, sure, you could do both of those, but then you have to connect that to here. But if you just remove one connection from this component is not connected electrically to anything else. There's no closed path with anything else. So that resistor is considered to be out of the circuit. right now. If you have a just a freestanding ohm meter, you can measure that. Now, if you're using oscilloscope to measure something else across that resistor or whatever else, then you might want to take the whole part out, because the oscilloscope sometimes is it's a floating ground, and sometimes you don't know if the ground is connected to something else. Okay, but if you just have a freestanding ohm meter, you can just lift one leg of the resistor. Okay, so that's what it means of de-energizing the circuit and removing the circuit, the component out of the circuit here. Okay. All right. Let's just keep going. Get the board ready for the next presentation here. All right. Okay. So remove the component first. So we took care of that. Common procedure: lifting one leg is often enough. Yeah. So I just described that thing. I just described that thing for you. Okay. And then measure using the lowest value. If you get the overload or over limit indication, then move to the next higher resistance range. Okay. So that's as far as the switching ranges. And here we explained that already a few minutes ago. All right. Open loop, over limit, overload, some different people call it different ways, means no continuity in case of the ohm meter. Okay. It can mean infinite resistance between two measured points, or other graphics, such as you can see two dots, two dashes, or something like one with the dot. Can be displayed if the measured value is greater than the selected range. Learn your equipment's ways of displaying things. Okay. Measuring continuity, testing for continuity. That is going to be this symbol right here. Continuity. Is this guy right here. There's my pointer. Continuity right here. Now, continuity is going to show you a little beep. Sometimes, quite often, most of the times, you're going to hear a beep. So let's switch this multimeter to a continuity tester. We're going to select the continuity tester, and what we're going to see is a little bit of tangling happening here. These are the probes for this multimeter. If you make contact with those probes, you're going to hear a beep. Sometimes quite annoying, but this way it just tells you that something is connected or not, if it's a clear path. So this screwdriver here is a metal. So, okay, yeah. Yes, there's a continuity between that. If this was broken, if the cable was broken or the wire is broken, it might show you no continuity, as it is right now. Right? So let's keep going. Measuring continuity. Testing for continuity is used to verify closed circuits, or closed or clear path, or 0 ohms path. If you measure something, I want you to remember this forever. I'm going to switch to an ohm meter with a range of up to 200 ohms. Look what is going to happen when I join those leads. It's going to show me about 0.6, it should show us 0 ohms, but there's a certain resistance in the lead, and maybe there could be certain resistance between the contact point. Maybe there is some oxidation happening. See what happens if I just rub those together to just clean those probes. 0.5, 0.6, see, we got it down a little bit, okay? But if we select it to 2000 ohms range, that should show us pretty much 0, right? 0.01, 1,000th of an ohm, okay? If I hold it tighter and rub it together, then yeah, we got 0 ohms. This reading here is 0 ohms. If you see that 0, please do not say that it measures nothing, okay? When it comes to this, I say to my students, nothing is not a word in a dictionary right now. Just forget about the word nothing, okay? It's 0 ohms, okay? When you join this, so there is no resistance. 0 ohms means that there is no resistance between those 2 points. It's not nothing. It's a continuity, clear continuity. Closed circuit, closed pathway, 0 ohms, 0 resistance, no resistance, but it is not nothing, okay? Then again, if you are going to separate those leads, you have a great resistance between those two. It's also not nothing. What do you measure? We measure infinite resistance or close to infinite resistance because air still has some resistance. But also, again, please do not say that you get nothing, okay? You're still measuring the resistance of the air, and it's so huge that in some cases it's actually considered to be infinite, okay? Keep going. This is what I just showed you, so I'm not going to go over that. Now, this component, this resistor here is completely removed from the circuit. So first de-energize the circuit, and somebody didn't de-energize the circuit here. Oh, Mr. Bach, okay. All right, this symbolizes removing the part, the component out of the circuit and connecting an ohm meter to it. But I just went over great detail just a few seconds ago of what I meant by that. Okay, now measuring the resistance. You basically put those probes against 2 leads of this component. Make sure you do not hold that with your fingers. You hold your probes right here. Do not touch the metal parts, because then you're putting your own body resistance in parallel with this resistor. Your body's resistance is not infinite. We do have resistance. We do have resistance between our hands. Okay? Let's just see what my resistance is today. I feel pretty resistant today, don't you? Okay. Going to select the highest possible range, which is 20 mega ohms, 20 million ohms. And I'm going to hold these probes in my hands, see what my body resistance is. Oh, look at this. Well, I can even go to 2 mega ohms. All right, it shows that I'm having some resistance. So because it's 2 mega ohms, so mega means times 10 to the 6th, so it's 2 million ohms, 2 million ohms. So whatever we see here on the display, we're going to have to multiply by 1 million because we're in the range of millions. So times 1 million, I got about 500,000 ohms across my hands. Okay. I'm holding those probes. About 500,000 ohms. So I do have some resistance. Let's see what resistance I'm going to have between right here and here. Oh, it's even less. 0.2 million ohms I have between this point and that point of my finger. I'm pressing really hard. Okay, so here's how you measure resistance. So if you are measuring high resistance or any resistance, just try to make sure that there's nothing else connected in parallel with this component that you're measuring. Measuring or testing continuity. quite often is being used to check the fuses. This is a fuse, and this particular one is 5 amps. It could be 2 amps, it could be 20 amps, whatever it is. But a fuse should have pretty much zero resistance, should have continuity across that. It's just rated for up to 5 amps. If the current through this fuse goes over 5 amps, then the fuse is just going to blow. It's just going to destroy itself. So nothing else is destroyed. The fuse is cheap, and the piece of equipment, whatever it is, could be very expensive. All right, keep going. Measuring current. Current amps is the flow of the electrical charge through a component or a conductor. Current is measured in amps or amperes, or amperes, depending on where you're in the world. You're going to call it different ways. Before measuring current with your meter, disconnect the power source. Place the multimeter in series with the circuit in order to test the current path. Forget the here. The full amount of measured current must flow through the meter. We're going to take a look at this in the next slide. If you attempt to measure current in parallel with the circuit, you will blow the fuse inside your meter. We're going to go over that too. Select the highest current settings range and work your way down for the most accurate reading. Go back to this slide after I show you this, the practical side of it. Reconnect the power source and turn on the circuit and perform the measurement. Let's see if we have some pictures happening here. Okay, so remember when we were measuring the voltage, we would connect across this resistor, we would connect the voltmeter in parallel with the load. Now, the amp meter, we're going to connect in series. Okay, so here's the amp meter. So the current path goes from the power supply through the amp meter where it's going to be measured, and then through the whole whatever else is connected, and it's going to close the pathway and it's going to come back to the power supply. Okay, so we have to let the current through. So through the amp meter should be connected in series with the circuit as opposed to in parallel. Okay. Now remember the internal resistance of a voltmeter. We are connecting voltmeter in parallel with the load, so we want to, the idea is to take a measurement without I'm just going to wait for the phone to stop ringing. Okay, so the idea is to take the measurement without affecting the circuit. Okay, so now how do we not affect the circuit? By connecting something in series with the whole current path. Well, ideally, the resistance of the amp meter should be 0 ohms. There should be no resistance. In reality, it is extremely, extremely low, just to make sure that we can take the measurement, but not affecting the circuit. Okay? So the resistance, the internal resistance of an amp meter is extremely low. So the measurement can be taken without affecting the circuit. That's ideally. Ideally, it should be 0. In reality, it has a little bit of a resistance, but it's insignificant. Yeah. Measuring current. If you do the same thing as we did with the voltmeter, connecting the probes straight to the 9-volt battery, because the amp meter has pretty much almost 0 resistance, then the current is just like shorting these two terminals together. We're going to have extremely high current flowing from one terminal to another because there is nothing to slow the current down. So if we connect anything, let's say this is a light bulb or a resistor, that's something that poses certain type of resistance just to slow the current down, then we can measure the current by connecting this amp meter in series. Let's analyze the seriousness or seriousness of that. The current goes from the red probe through the light bulb through the power supply, it comes back here. Or from the power supply, it goes, this is the electron flow, okay? So there are two ways of analyzing circuits. One is the electron flow, and the electrons flow from negative to positive. And the other one is the conventional current flow, where we're assuming that the current flows from the positive to negative. Either way is fine when you're analyzing the circuit for the purpose of calculation, but if you're calculating the circuit, choose the convention and stick to it all the way through the calculation. So you're either going to choose conventional current flow or electron flow. These arrows here showing the electron flow. Okay, so let's see the power supply here. The electrons flow from the negative terminal, go through the amp meter, which is supposed to be zero resistance, just enough to take the measurement. And then it keeps flowing through another probe, through the light bulb, and comes back to the power supply. So that's connecting the amp meter in series. Okay. Review, a bit of a review here. Ammeter, so that's for both lectures, yesterday's and today's. Ammeter capable of testing voltage, current, and resistance is called a multimeter. Okay. Cool, eh? All right. When measuring voltage, the multimeter must be connected to 2 points in a circuit. Be careful not to touch the bare probe tips together while measuring the voltage, as this will create a short circuit. Basically, if you touch those, sometimes you're going to work in tight spaces in the printed circuit boards. You just have to make sure that you don't short things out. Shorting things out, let's just explain something here. What's a short circuit? What is a long circuit? Well, there's no such thing as a long circuit. There's a short circuit, or there's an open circuit. Okay? If you have a battery with terminals, let's say this is plus, this is minus, this way here. If you connect a straight wire from one to the other, you are shorting this circuit. You're shorting these two terminals. Sometimes we want to short things together, and sometimes short is a failure. Okay, let's say, where's my other cloth here? There it is. Let's just say we have a resistor in a circuit. Okay, so here's the power supply, and here is a resistor, R1. Plus, minus. Let's keep conventional current flow. So we're going to go from positive to negative. Now, if you connect too much voltage to this resistor, more than it can handle, something is going to happen. Excuse me, the resistor is going to blow. Right? So that means something's going to get damaged inside the resistor. The resistor can be shorted inside. So that means there's a short here. Another thing can happen in the resistor. If you put too much current across R1, too much voltage, too much current is going to cause too much current. Something might happen that the resistor is going to blow and it's going to open. Okay? So that means there's an open circuit. Short circuit versus open circuit. Okay? Terminology that you need to know. Let's keep going. All right, when measuring voltage, okay, so make sure that you don't touch anything else. So sometimes you have to be careful of what you touch when you're taking in a measurement, okay? Never read resistance or test for continuity with a multimeter on a circuit that is energized. We went over that. Make sure that you know how to de-energize the circuit. Sometimes capacitors still hold the electrical charge after the power supply is disconnected. Right? That's a big one here. I put it in red. When measuring current, a multimeter must be connected in series with the circuit because we need to pass all the current through that amp meter. So the current can flow through the meter here, okay? Multimeter in voltmeter setting, internal resistance is high. because we are tapping in parallel. So we need to have the resistance high, so as little as possible current flows to the point that it's insignificant. Again, the idea is that to take the measurement without affecting the circuit. Multimeter in amp meter setting, internal resistance has to be low, because then again, if we want to put something in series with the whole current path without affecting the original purpose of the circuit, then you need to have whatever you put in series, you need to have that the resistance of 0 ohms as close as possible. Okay. Keep going. Right. Then we have clamp-on meters. I'm going to show you how one works. I have one right here. Okay, I do have one right here. And I'm going to demonstrate how it works. But let's just keep going with this. We're almost done with the PowerPoint here, okay? All right, so clamp-on meters. A clamp-on meter provides the ability to measure the current without having to break into the circuit to do so. So that means you don't have to put that amp meter in series with the circuit. You clamp onto the wire. Okay? The wire, how does a clamp meter work? If you have a wire, so you have a wire. All right, you have a wire here, and there's a current flowing through this wire. If the current flows through this wire, you are going to have something that is called electromagnetic field going through this wire. It's like in a spiral way, and it's going to go this way, just like the corkscrew. And the wine drinkers here, you turn the corkscrew, it goes that way, and the screw element moves that way. So that's electromagnetic field. If you clamp on with the clamp-on meter, you're putting a coil. The meter, okay, here's a readout, okay. The meter has a coil here, just right here, okay. It has a, okay, I'll guess my face. This here is a sensing coil that is going to sense the strength of this electromagnetic field, and based on the strength of the electromagnetic field, it's going to do its calculations and going to display the value of the current. Pretty clever thing. So how do we do that? Let's say this is a wire. We open, see here, we open the clamp, put it around the wire, and that's, if the current flows through this, if this is a wire and the current flow through it, then it would cause electromagnetic field. This element would sense that, and would be this, the value of the current would be displayed here. So that's all about the theory, sort of surface scratching theory on the clamp-on meters. And we're going to take a measurement. I'm going to show you how this works. I have a light bulb set up here, right here, okay? I'm going to turn this on, and we're going to measure the current. We're going to calculate the power that is dissipated across the light bulb. Pretty cool. Okay, keep going with that. So that's the idea of a clamp-on meter. Other testing devices. Circuit tester. This is a circuit tester. Every electrician's best friend. After you do your installations, you just plug those in, and these lights here, depending on how they light up, they're going to tell you whether everything is okay, if you haven't reversed polarity of anything, or if it's working at all. Okay? Read the instructions when you get it. Here's the instructions on how this works. Okay, depending on which lights light up, there could be everything okay, or there could be a trouble somewhere. Okay. Testing probe, very, very interesting device, very useful device. Non-contact voltage tester. If held close to a power circuit, it will detect the voltage and indicate by the way of a light, or some of them is going to give you audible sound, so you can hear the beep. Caution needs to be shown. Caution needs to be shown when using this type of device. It must always be verified. Let's say the battery runs out inside that probe, and you're going to bring it close to the circuit, to the hot terminal of this duplex receptacle, and it's not going to light up. Well, you would assume that that there is this receptacle is not energized. So make sure you test it on a live one, that is live, to make sure that it works before you start testing on something that you're going to work on. Okay. And that's the end of this PowerPoint. Now, let's get some cool stuff going on here. I'm going to show you, we're going to show you a few things. What I have here is I have few nice toys. I have a power supply that I have set up the voltage to 5 volts. Okay? And then I have a couple of meters. So let's just disconnect the voltmeter here from this whole circuit. Here and here. This is an old voltmeter. Okay, now let's disconnect the amp meter here. What do we have? We have 3 resistors connected in series for this testing purposes. Come on. We're back. Okay, I think I just took a picture with the camera here. All right, so now we have 3 resistors. This is how the breadboard works. These lines here are connected. So when I put this resistor, can we zoom in a little bit more? Sure we can. Focus. If I put the resistor in this column right here, since vertically they're all connected, it's just like touching them like that. That's how the breadboard works. All of them are connected this way, but this column is not connected to that. This is just, they're connected that way here. Now on the top here, you got the rails, the power rails, they're connected that way, horizontally. Okay? And the line indicates how they are connected. Sometimes you're going to see ones with broken lines. That means there's this section is disconnected from that section. So you just take a wire, stick it here, and take a wire, stick it here, and you have continuity. Okay, so this resistor, it's a 330 ohm resistor. There's another 330 ohm resistor, and there's another 100 ohm resistor. So what do we have in series? If we connect the whole thing in series, we're going to have 330 plus 330 plus 100. So 330 times 2 is 660 ohms plus 100. So across this whole circuit, if we connect it in series, we're going to have 760 ohms. 330 plus 330 plus 100 equals 760. Okay. Now you can see that this circuit is not complete because this is not connected to that. Well, what are we going to do? We're going to connect an amp meter to that. Here is an amp meter that we have. Right? It says milliamperes. It has 2 scales or 3 scales. One from 0 to 250, one from 0 to 100, and one from 0 to 50. Okay, so let's see how this is going. And it has ranges. It's a switched range. Now this is up to 1 milliamp, up to 5 milliamps, up to 10 milliamps, and so on. And here is a short. If you connect that, then you get a dead short across these 2 probes. They are polarized. Okay? Here's a positive side of that. Can we see that? And there's a negative terminal of this meter. So let's connect the milliamp meter across so we can complete the circuit. All right, we have broken the circuit right here. So we're going to connect, okay, here's a positive, here's a negative terminal of the power supply. So how are we going to polarize this meter? We're going to polarize this meter so the positive goes to the positive side, and then the negative goes to the more negative side of this circuit. So over here, when the circuit is broken, this would be the positive side of the circuit, and there's a break right here, and this is the negative side of the circuit. So just match the polarities. Okay, I'm going to put this one here, and we're going to put the negative right here. So now what we have a current flow goes from the power supply through this resistor, through that resistor, through the amp meter, and then through this resistor, and comes back to the power supply. Do we have any current flowing here? Oh, look, we're showing some current flow in this. All right. The needle has swung. What do we have? We're in the range of up to 10 milliamps. Right here, see? And we have something almost 6. Now, let's just de-energize the circuit for a sec. Okay, do we have a complete 0? No, we don't have a complete 0 here. So sometimes those analog meters, sometimes you just need to calibrate. So you will just turn this screw here, it's a calibration screw. Okay, here. Now we have the needle at 0. Now we energize the circuit again. See what reading do we have? We have a range of up to 10 milliamps. Do we have a scale that says 10? No, we don't. But we do have a scale that says 100. Okay. So what you do is you take this range, which is 10 milliamps, 10, and divide it into 100. So 10 divided into 100 is going to be 0.1. So whatever shows here on the scale, you're going to multiply the reading by 0.1. Now, what we have here, we have some bad connections. This is an old meter here. So 60 times 0.1 is going to be 6. 6 milliamps, because these are milliamps. So 6 times 10 to the negative 3. So 6 1,000ths of an amp. That's how you read this. Okay. Now we also have a voltmeter here. This one here. And we're going to connect this thing right across the power supply. Right across. So this is where our power supply is applied right here. Okay. So this is our positive, this is our negative, and we're going to connect it right into the terminal here and the other terminal here. I'm just going to touch it a little bit just to make sure that the polarity is okay. Look what would happen if I reverse the polarity on, let's see here, that's where it goes. If I reverse the polarity on the analog meter, I'm just going to touch it briefly. The needle tries to go the other way. And if I held it for a longer period of time, then I would just burn down the element right here. So polarity is important while using analog meters. Okay, this one goes here. This one goes right across the power supply. All right, so what do we have here? What does this one show? We have up to 5 volts range. Let's see what is the closest thing that we have to 5. Well, we have a 5-volt range. So basically, we don't have to do any multiplications or divisions or anything like that. The needle has swung full swing on the 5-volt scale right here. Can we see it? Okay, there's the needle. That means it's showing pretty much 4.9 volts, but I'm not going to, this is not very accurate piece of equipment. It's probably 50 years old now. Okay, so this meter shows, the meter, internal meter on the power supply shows 5 volts. I probably would trust this more than that right now, but let's take a look. I'm going to set this multimeter. Let me just, here. I'm going to set this multimeter as a voltmeter. So we're measuring 5 volts. What's the range we're going to choose? We're going to choose 2 volts? No, because 2 volts is not enough to measure 5 volts. So the range of up to 20 volts right here is going to be the next higher. So that's going to give us the most accurate media reading with this multimeter. So let's just connect. And let's see what this one shows us. I'm going to turn this off. That's the probes for this one here. Okay. So I'm going to connect that right across the power supply. Here and here. And that is going to show us 5.02 volts. So it's pretty much more accurate than, I would say this is about 5 volts. This one shows us 4.9, but I'm going to trust this multimeter more. Now, yesterday I said that sometimes you might want to choose an analog multimeter. I'm just trying to hold it with my hands here, trying to make a better contact. Let's see here. Okay. Here, I'm holding that. We get the voltmeter happening. Okay. What happens? See what happens if I de-energize the power supply. The power supply is not going to. It's going to shut down, but the voltage is going to disappear gradually. Look what happens. Observe these two right now. This shows the current. This shows the voltage. And see how this voltage behaves. You can see how things behave while using the analog indicator. Now, take a look at this. Are you going to be able to tell what's actually happening on the digital multimeter? It just shows you some bunch of numbers. Do you remember what was what? This gives you a better indication. So sometimes, yes, you might want to prefer analog indicator versus digital. That would be the best example of that. Okay. Turn it back on and turn it off. See? Okay. So that's why I said that sometimes you might want to use the analog meter versus digital. Okay. Now what I'm going to show you, I'm going to disconnect this little circuit that we have. And I'm going to get you something else. Remember I was talking to you about the LEDs? The LEDs. Let's get the laptop here. There's a website that I pulled up, the voltages, the forward bias voltage of the different colored LEDs. Okay? Now, in order to have different light appearing on LED, that diode has to be made out of different materials. And when you put those two materials together to make a semiconductor, you need to apply certain type of voltage to cause certain amount of current before that thing, the diode, lights up. Okay. Where do I have my little circuit here. I just had it in front of me. Okay, I'm going to stop the video here until I find the damn thing. Oh, here it is. No, I don't have to. It's just in front of me. So I have put few LEDs together, different colors, and we're going to take a look. We're going to measure the forward bias voltage. The forward bias voltage is the voltage that is going to cause a minimum current to light this up, the LED up. And once that forward bias voltage reaches its nominal point, it's going to stay there. That's how the diode works. Forward bias voltage, once it gets into a diode, it stays there. The voltage across the other components that are in series might change if you regulate the whole power supply, but the voltage across the diode is going to stay. So we have a few diodes here. Now, let's turn on the meter. Let's make this meter a continuity diode tester. So it's this little symbol here. Here is a diode tester right here. It shows a symbol of a diode. Okay, so let's just turn the dial onto the diode tester. Okay, so in the description of how things work, this should tell us the forward bias voltage of the diode if we polarize the diode properly. So here is the positive side of the diode. Here's a general purpose diode. Looks like a size of a resistor. And it has a little tiny band, like a stripe here. So that's a negative side. That's a cathode of the diode. And here's the positive side. That's an anode of the diode. Okay. Now let's take that diode out of the circuit. So it just sits right on its own. And we're going to forward bias that diode. This is a silicon diode. It should have 0.7 volts when it's forward biased. So here's the positive, here's the negative. Let's touch that, see what happens. Well, this one shows almost 0.6. So it's close to 0.7 of forward bias voltage. Let's take a look at other ones. The red LED, and you can tell that the forward bias are because the LED is going to light up a little bit because the continuity resistance and diode tester introduces a little bit of voltage across the probes. Okay. So let's just take a look at what is the forward bias voltage on this. This one shows that this diode should have 1.6 forward bias voltage. Let's take a look at the table here. Red, 1.8. It should have 1.8. Again, what do we have? 1.6 did we have? So this was pretty close, almost 1.7. Okay. Now let's see what we have for the yellow. The yellow should have about, well, 2.2 volts. Okay, let's measure the yellow. 1.8, almost 2. Green, 1.8. What does the green show? 3.5. Oh, something is not right. Oh, well, then maybe we should not trust this meter. It says that it's going to do that, but does it? Okay, let's keep going. Blue, it should have 3.6. Does it? Ah, it says we're out of range. And the white, well, let's just make sure that we didn't reverse polarize it. Nope. Let's see the white one. Still, it lights up a little bit, but we still get no reading. Maybe the meter is not capable of testing certain diodes. Okay. So let's make another experiment. The forward, as I said, the forward bias voltage, once the diode reaches that, it's not going to go over. Okay? So let's energize this circuit. And the way we're going to energize this circuit is we're going to apply 5 volts. Here's our power supply, 5 volts. And that is going to go to the this negative part is going to go to the cathode, and all the cathodes are connected together. Okay. And then we're going to connect the positive side to the resistor because we want to limit the current. If we just connect the power supply straight to the diode, we're going to burn the diode. Okay. So let's see what we have across the red LED. We just made a red LED light up. That means it's part of the circuit. Now I'm going to change this into a voltmeter. So let's see what voltage we have across the diode. We have 1.8 volts across the red diode. And red diode 1.8 volts. Oh, that's pretty cool. Let's see what we're going to have on the yellow diode. So we're just going to change the supply to the yellow diode. We're going to make that light up. What do we have on the yellow? We have 2 volts. Yellow, 2 or 2.2. That's pretty good. Close enough. Let's see what we have on the green. Made the green light up. Okay. Got 3.35 volts across the green diode when it's in the circuit. 3.3, 3.5. Oh, we're getting close. That's closer. Then let's do the blue. Okay, here's the blue diode. 2.77, 2.8. This was not very accurate. So there is something. Maybe there's a different manufacturer here. Right. Let's continue with the white. Always verify things. This one looks like it's a warm light, warm white. What was voltage we get? We get 2.68. Okay. And on the white we should have 4. So different literature is going to tell you different different amount of forward bias voltages. It's not like a one fit all. Obviously, what we just shown here, we demonstrated that different manufacturers can produce different devices in a different way. So always verify, always know what you have. Last thing I'm going to show you. Oh, wait a second. We haven't checked the silicon diode yet. Okay, so let's check. This is just general purpose silicon diode, and we're going to connect that in the circuit. Okay, I think we still have it connected. No, we don't. And we're just going to connect it anywhere in that rail. So now we should have current flowing through this diode and through this resistor here. So let's see what the voltage is going to be. Oh, we got 0.69, so it's like 0.7 volts. That's right. Okay, so silicon diode should have 0.7 volts. Okay, now last thing I'm going to show you, as I promised, the way of how this clamp-on meter works. Okay. Sorry about the telephone call, but I'm in the office environment, so we're going to hear that sometimes. Okay? It's just how it works here. Okay, so now what do I have here is a light bulb. We have a light bulb here. I'm going to turn on the light bulb. Yeah. Okay. Now, the light bulb is connected with an extension cord, portable cord, just like that. So let's see if we can get a reading while turning the light bulb on. Can we see the light bulb difference in the lighting here? Maybe you see a little bit. See on the edging? Okay. So what I'm going to do is I'm going to it just turned itself off. Now, here. Let's see, because this is also a multimeter. You don't always use the clamp-on side, but you can use the ports here to measure other things like voltage or current. And this would be an auto range. You just select the function and then the meter selects its range, or you can just toggle the range here. Okay, so let's make this thing, because the light bulb is connected straight to the outlet, and there's about 121 volts I measured this morning that was in the outlet. So let's switch this thing into an AC amp meter. So that's, we have that. And that means we are going to use the clamp here. Okay, just like that. So let's get some focus happening. I'm going to clamp on this clamp-on meter onto the wire. It's just going to pass through. Here. Just turn this off. I'm going to clamp it on, just like that. Open it like this and clamp on. Originally, without anything, it shows a bit of a noise here, 0.06 of an amp, and this is just the noise that this coil is picking up. So now we're going to clamp it onto a wire, and we should see some current flow, right? So let's turn the light bulb on. Light bulb is on. Okay, let's clamp on the meter. What do we see? We still see 0.06. So it's as if nothing has happened. Oh, wow. How could that be? Well, let's see how could this be. Why is it that we don't get any reading? Well, one of the wires is conducting current one way. The other wire is conducting the current the other way. This one here causes the electromagnetic field to have this direction. The other one is just the opposite. It's causing it that way. So the magnetic field in one wire, the supply wire, and the magnetic field that is on the return wire, they're of the same strength, close to each other. They just cancel each other. So you have to know how to measure this. Let's see here, because what I did is I have this whole extension cord here. I split it. Okay, there's one conductor and one conductor here. Okay. So let's turn the light bulb on again, and it's just put the clamp on just one of those wires and see if we get any reading here. Okay, so here I'm going to clamp on only one wire. Oh, we get something that's 0.25, quarter of an amp. Yeah. Now this is too close to the monitor that I have. Let's just a little bit further from the monitor, so that just to get the interference out. Okay, now look at this. It's showing about 30, 35, 30, 0.36 of an amp. So let's say 0.35 of an amp. Okay, well, let's just take a look at something here. All right, the current is I, current equals 0.35 amps. Okay. The voltage is 120. Well, I think I measured that it was 121 volts. So let's just stick to 121 volts. Okay, square brackets. Okay, what can we do with this? What's the formula for power? Power equals voltage times current. Now someone will say, wait a second, we're dealing with AC. That's okay. Yes, we are dealing with AC, but we're dealing with the RMS values, so you can apply this. You can apply this formula. I'm not going to test you on the RMS right now, but you're going to have that. I'm showing you the meters. So what's the power of the light bulb that's dissipating the power? Power equals 0.35 times 121 equals, let's see if we can get a calculator here. Okay, let's see, 120, okay, 0.35 times, where's the, okay, times 121 equals around 42. 42.35, so let's say 42, and that unit is going to be watts. Oh, yeah. Power equals 0.5, so that equals 42. Unit is going to be watts. Well, I bought 2 of those light bulbs. Actually, here's the package from the light bulb here. What does it show? It shows a 40, this is a reverse thing here. This package is showing that this is a 40-watt light bulb. Yeah. So it looks like the meter works. So we have gone over the basics of the meters. You should know how to measure current, you should know how to measure resistance, you should know how to measure voltage, and you should know how to select the range. If you have any questions, by all means, send me an email. But this concludes today's lesson. Okay? I'll see you when I see you. I got to end this thing here. That's the end button.